So the title of this talk is Efficient and Long Context Generative AI Models. So by generative AI models, I'm referring to like language models and text-to-image synthesis models and so on. But we'll be focusing mostly on the language models. So the GenAI models are now integral parts of many real-world applications, from like a chatbot, like a virtual humans, like search engines. So almost all the software these days have large language models that are being integrated into their system, right? But there are some practical challenges that are hindering more widespread adoption of these GenAI models or language models in real-world applications. And the first thing is the high operating cost. So basically, it takes a lot of just money to train the models and also serve them, even if they are like open source models, right? And they also have very limited context size. So the state-of-the-art language models can only fit up to like 2 NeurIPS papers in their context. So there are some like limitations on what kind of application that they can serve. Okay. So to lower the operating costs of the GenAI models in production, such that they are more widespread, so that they are going to be adaptive more in industry, we need to enhance their efficiency. But the efficiency regarding both the training and serving the models. So if you consider the training costs of different large language models, so it's just going up. It's skyrocketing. So it takes about like $100 million US dollars to train the latest models such as Gemini. And also when serving the models, even if it's just a smaller like a Llama 3 models, per hour, right? If you serve the largest Llama 3 model, it's going to take about $200 per hour, right? And these costs could be excessively high for like startups or small to medium businesses or anyone. So that's actually making the GenAI adoption to be mostly happening by the big tech companies and the companies with like a sufficient capital. So to lower the barrier and make GenAI to be more accessible to everyone, we need to enhance the efficiency of the GenAI models. The another thing is that we also need to increase the size of the context window. So we want to solve some challenges that are not really solvable by humans, right? Like such as this. Right? So we want to like summarize all the papers that have been published at AI conferences this year, such that it can write a report about the current AI trend and predict what kind of topics will emerge next year, right? And we can also like summarize all the legal documents and then provide some legal consulting, right? So there could be like relevant cases, like laws and regulations. So these kind of very complex tasks cannot be solved by the current generation of the large language models because of the limited context window size. So there are like some techniques that can make up for that, such as like retrieval augmented generation, but even their performances are limited by the context size. So, increasing the context window size of the GenAI models is especially important for the enhancing the performance of like multimodal foundation models and retrieval augmented generation. For current like multimodal language model, they can only process up to few small images. But if you want to have a better answer, right? So the images, because they are like a continuous, in continuous domains, we can like represent them in different resolutions. If we want to like process high resolution images, and if we want to like handle multiple images or like even videos that come in like a really large number of frames, then we'll need to deal with a larger context window because they should be represented with more number of tokens, right? And also for retrieval augmented generation, the success of the retrieval augmented generation system depends on the size of the context window, because suppose that the correct answer is within in the maybe 6th or the 7th in the retrieved document, right? But the context window is so limited, so it can only take up to process up to 5 documents that have been retrieved, right? Then it's not going to find the correct answer, right? So having larger context window size will increase the recall of the retrieval augmented generation systems, such that it enhance their performances. But the problem is that as the context length goes up, the efficiency becomes more of an issue, right? Because the current GenAI models are based on the transformer models, and the transformer models have quadratic attention mechanism. So the time and space complexity of the model will go quadratically with the input context size, right? So we need a way to deal with this complexity. Okay, so when enhancing the efficiency of the GenAI models, there are 2 aspects that we can improve on. So first is the training efficiency of the GenAI models. And the recent GenAI models are extremely large in number of parameters, and they are also trained on huge data sets. So it means that it's almost impractical and infeasible to train them from scratch, and especially in academia or in startups where we have very limited computing resources. So we need parameter and sample efficient training approaches to train them. Okay, so I'm exploring 3 different directions in order to achieve the training time efficiency for GenAI models. First is the neural weight generation, where we generate the neural network weights instead of actually updating them in the original parameter space using the gradient-based updates. And the second is the dataset distillation or pruning to make it more sample efficient. So we can reduce the number of the samples that the model should be trained on. And the third is some kind of AutoML techniques that can reduce the search cost for the optimal design or optimal hyperparameter configurations. Okay, so I'm going to talk about the first one, the training-free neural network optimization. So this is the idea that we had, right? There are so many pre-trained GenAI models that are publicly available, right? The language models and text-to-image synthesis models that are all available on Hugging Face and GitHub repositories. So why should we train them from scratch, right? Or why should we just select one and fine-tune it, right? So we can just try to learn a latent representation space from those publicly available pre-trained GenAI models, right? And this opens up a lot of possibilities, such as neural network generation or latent space optimization. So our idea is to learn the latent space of all these pre-trained transformer models, okay? Especially for the focusing on their weight. So we have proposed a framework for neural network generation based on the diffusion models. So this is basically similar to the image generation model based on the diffusions. But there are 2 different steps to achieving this goal. A neural network is composed of its architectures and parameters, right? Architectures and weight. So we can generate a neural network by first generating the architecture based on the data or the task, and then generating the weights for the generated architecture. So we take a 2-step approach, and we can generate the neural networks for computer vision models in such a 2-step approach. But for language models, the architectures are kind of the same, right? They are fixed to some transformer-based architectures. And also the computer vision models are also converging into the vision transformer, etc. Right? So we are now focusing more on the neural network weight generation part than the architecture generation part. But okay. But to just give you some idea of how we can do the neural network generation. So we, in this year's paper, ICLR paper, we proposed a diffusion-based neural architecture generation framework that generates the computational graph of like computer vision models such as CNNs to generate the task optimal architecture, given some data set, right? So the idea is very simple. So we learn the graph diffusion model that generates the graphs, right? But instead of just generating them in an unconditional manner, we generate them based on the data and the device encoding, and then use the performance predictor to guide the generation process. So this is basically a guided diffusion process, which allow us to sample from a region where with high accuracy, or we can sample the architecture with lower latency. So it's a plug and play framework, such that you can plug in any predictor. So we can plug in the predictor for the accuracy, we can plug in the predictor for the latency, we can plug in a predictor for like robustness, right? And as you can see here, it allows us to sample a better architecture compared to just sampling at random in an unconditional manner, or sampling conditionally, then filtering using the predictor, right? So the guided diffusion is more efficient in exploring the latent space for neural architecture generation. Okay, then we are going to move on to the sampling of the neural network weights. So why do you want to sample the weights instead of just deterministically search for a single set of weights that work well, right? So that was the question that I got received a lot when giving talk on neural network generation. So there are like a certain regions, right? So first, the randomly initialized weights are not that effective. So you know the low-ticket hypothesis, right? So most of the weights that have been initialized are initialized in a poor region. So they never, some of the weights never get trained, never get updated during the course of training. So they do not really contribute to the performance. They could be just a cut, and it's not going to affect the final performance of the model at all, right? And the second is a model ensemble. So if we want to sample weights, then that means that we can have multiple set of weights for the same latent space, right? For the same latent feature, right? And we can ensemble them together to obtain even better performance. So I'm going to show you an example of model ensemble later in the slides. And another thing is that we are also exploring a way, like a learning paradigm called self-evolving AI, which is based on the population-based search for the optimal models. So in this learning paradigm, we'll have to have a population of neural networks, right? And we are going to use some crossover and the mutation across like a different hypotheses to obtain even better hypotheses. So this could be applied to the search for the optimal architecture or search for the optimal weight. Okay. So in our latest work on neural weight generation, we propose a neural network weight generator framework that is basically based on the latent diffusion model, right? So we first train an autoencoder that can encode the vectorized weights into some latent code and decode it back to the original weight. Then we train a diffusion process that can generate the latent code that can reconstruct the weights for a given data set encoding. So this is a conditional latent diffusion model, right? Then at the sampling stage, given an unseen architecture and unseen data set, then we'll be able to generate the set of weights. that will work the best for that given data set and architecture combination. So these are the accuracy comparison of our method against like a GHN. It's a graph hypernetwork that generates the architecture and the neural network weights at the same time, proposed by like Meng and Ren. And we can see that our method works a lot better. So a little bit of improvement on ShiftWire 10 data set, but a lot more improvement on the ShiftWire 100 data set. But you may wonder whether this will actually scale to like a large foundation models. So I'm going to go to that later. But we can, by looking at the results on this like small computer vision networks models, we can see that in some cases, it can obtain a model that has 100% accuracy right away, right? Oh, sorry. But in some cases, in many of the other cases, sampling an optimal weight for an unseen architecture and unseen data set is very difficult, such that we generate a weight that perform a lot better than the randomly initialized weights or the weights that are obtained from weights from a network that's trained on another data set, right? So we can see that this will allow us to reduce a lot of training time to get to the optimal solution. So for instance, compared to the pre-trained model on this Japanese character recognition data set, I mean, the pre-trained model will take 50 epochs to train to obtain the target accuracy of 60%. But our method only takes about like 15 epochs. So neural weight generation allows us to start from a better initialization, so it can actually reduce the time until the convergence to the optimized solution. And so this is a way to reduce the training time, right? So we can enhance the training efficiency using the neural weight generation. Okay, but so we also have tried applying the neural weight generation for the generation of the large language model weights, but because generating those weights could be so much expensive, instead of when we try to generate them in a dataset dependent manner, so we try to generate the LoRa weights instead for the large language models, and we can see that they do obtain much larger, higher performance compared to the baselines, even better than the one that's the LoRa that's obtained by LoRa on the actual fine-tuning on the target data set. And another thing that we can do with the neural weight generation technique is upcycling. So previously, there's an upcycling technique that simply just copies the weight of the large language model and then use it alongside the original weight, right? But instead of doing that, we can do a similar thing by using the sampled weight from the neural weight generation framework that we have. And those models have achieved top places, the top place or the second best place on the Open LLM leaderboard. So we can basically just search for the optimal neural network by resampling the weight using some small validation set. And that is completely training free. So we don't have to train anything, right, on the data set. We don't have to do the update in the original parameter space. Just sample and validate. And that's the only thing that's necessary in search for the optimal model. So what we want to do further is that, because in the previous approaches, right, even if this takes so this takes a lot less training epochs, we still have to work in the original weight space to do the gradient-based updates. But we don't want to do it anymore. So I mean, maybe we can do the optimization in the latent space itself, then it will be much better. But the problem is that there's no way to do the optimization in the latent space if we don't project the weights back to the original parameter space. So what we have actually built is the performance predictor that can work in the latent space. They can predict the performance of the model on the target data set just using this latent embedding of the encoded neural architecture. So this predictor can guide the generation of the weights in the latent space, and also it could be used to do the optimization in the latent space. So we basically optimize just search for the optimal architecture in an iterative manner to the direction where it increases the predicted performance by this predictor. So that is the latent space optimization that we are working on. So I'm moving on to the next topic of efficient video representation learning. So as the video representation learning, video is increasingly adapted as one of the modalities for like a multimodal foundation models. There's like a more computational resources and requirements that are being put in processing the inputs, right? Yeah, but the video representation learning is really crucial for learning about the physical world. So it can let us to know about the physics, like motion, and many other the cause and effects in our world. So it could be also used as a world model. It has more knowledge about the world than just the one that could be described in text. Yeah, but with a prohibitively large amount of the computational requirements and the resources that we need to put in order to learn the representation for the videos, so we'll need a way to efficiently do the video representation learning. But if we can focus on the videos, then we can see that there's some temporal redundancy across the frames. So the video tokens are not equally valuable to reconstruct, right? So in the previous works, there's such a masked video autoencoding. So they just randomly masked out some part of the videos, spatially or temporally, and then made the autoencoder to reconstruct the part using all the context information. But this way just put a hole in some random places in the background. So we came up with a very simple idea of focusing on the part where there is any change across the frames, right? So we can consider this as a part where actual motion information resides. So we could have used like a flows or the optical flows or predicted optical flows, but we just made use of the differences in the original frame space. But this scheme works pretty well. So we can see that we can reduce the computational requirement to train the model a lot, about like 50%. And in order to, and if you just consider the memory consumption, so this is the video mass autoencoder, and these are our models. So there's about like a four times reduction in the memory consumption, right, to achieve the same performance. So we are trying to make this video representation learning to be even more efficient by working in the latent space rather than in the original video frame space. Okay, another thing is that for video representation learning, so there are many cases where we need to continuously train on the streamed data. And the semantics of the videos or the alignment across different modalities, like the video and audio modality, could change over time. Like for instance, in the past there could be like the audio between the car visuals and the sound could be very different from some of the electric cars that in this year, right? Like a Tesla or the gasoline-based cars, we have very different sound, right? So that shift in the audio domain could happen over time. And there's another thing that we can consider is there's a very sparse correlation between the audio and visual pairs. So in the video domains, there's very sparse information, right? Especially when you want to do the multimodal representation learning, right? So we can basically just do the unimodal representation learning and only focus on those very sparse correlation where actual like a correlation happens between these two modalities. So that's what we did, exploited for this continual representation learning. So and for more efficient video representation learning, in the future, we plan to work in the latent representation space of the videos that's obtained using the encoder and decoder architecture, like the one that could reconstruct the videos using like the 3D CNN, Coder CNN, like the one that's being used by the Sora or the Open Sora. And then we want to do the like a next frame prediction or the mass auto encoding, focusing on the only the residual part between 2 frames, using the same techniques that we have proposed previously. Okay, so I'm going to move on to the next topic of how to do the training in a sample efficient manner. So there are 2 techniques that are being used for this. So first is the dataset distillation. Second is the dataset pruning. So dataset distillation is going to condense the multiple samples into one to make a smaller dataset. And the dataset pruning is going to prune out some of the samples that are less informative in order to obtain a smaller dataset. So they are kind of like similar in their goal, but the techniques are different. So we propose a label-free self-supervised dataset distillation method this year that learns like representative images and their corresponding representations for efficient pre-training that could be used for many different tasks. So this is more a kind of a new approach because previously the dataset distillation techniques were kind of task-dependent. So they were trying to obtain the like a condensed data set for the label data set, right? So here it's more like a label-free data set distillation approach that minimizes the MSE between the representation of the model that's trained with the data, distilled data, and the model that's trained with the full data. So we don't consider the label. We only consider the distance in the representation space after we train on the distilled data set and the original data set. So we can see that actually there's like not much difference between the distilled data and the original data. And we can see that this approach obtains a lot better performance than the baseline approaches for dataset distillation. But this is only applicable to the image domains where we can actually condense images into one. So for the language models, we are exploring more of the dataset pruning approaches. And we are just also exploring ways to do the dataset distillation for the language domains as well. So another way to enhance the sample efficiency for the both language and image domains is by pruning the redundant samples while maintaining the efficacy of the training dataset on the full dataset. So the problem with the previous approaches for dataset pruning is that they are based on a single criterion, which could result in biased data selection. So that means they could obtain a smaller dataset, but they are so biased, so they don't really match with the distribution of the original dataset. So they just lack diversity of the original dataset. So what we did was very simple. We just clustered the dataset data using like a k-means clustering, right? Then we did a dataset pruning within each cluster, such that we remove the samples that are mostly redundant, and also we remove the clusters based on the transferability across the clusters. So if one cluster could be represented by another cluster, then we keep the cluster, right? If some of the clusters are not that representative, we also remove those clusters. So by just considering computing the transferability of each cluster by computing simply the cosine similarity across the cluster. And that, so this is just on how the knowledge from each cluster can facilitate the learning in other clusters. And this very simple approach could result in very high performance. So this is like a time cost that includes both the pruning and training costs. So the problem with the previous approaches is that they take so much time to prune the model. So even if the compressed data set expedite the training, if we consider the total cost of the computational cost, they're actually worse than random. So random pruning doesn't have any computational cost. So it works better than the others when we consider the time budget, right? But our method is so simple. It's based on the cosine similarity, came in the clustering, so it performs much better when considering the performance and time cost trade-off. And if you look at the combination, the selected clusters, they have the meaningful combination of the concept and skills. Okay, so a little bit more discussion on the efficient training part. So the training efficiency not only comes from making the algorithm to be more efficient, but we should also reduce the total cost in building these AI systems, right? So we want to minimize human efforts in designing the models, or finding the optimal hyperparameters, because they could this repeated search for the optimal architecture, design, or hyperparameter setting could take a lot of trial and errors. So neural architecture search and hyperparameter optimizations are really important when considering the efficiency in AI development. But neural architecture search is becoming less of a problem as all architectures are converging into the transformer-based architectures. So the hyperparameter optimization could be considered as more important these days. So there are several important hyperparameters for GenAI models, such as rank for the LoRa, and the scale hyperparameter for rotary positional embeddings. In addition to the conventional optimizer hyperparameters such as learning rate and weight decay and so on, that have large impact on the final model performance. So we want to search for these hyperparameters at the same time. But the previous approaches to hyperparameter optimizations are kind of costly, and they do not really generate across data sets or tasks. And they don't really consider the efficiency or the time cost. So they are automated, but they could maybe they may be more efficient than just a grid search or the trial and error process, but they are not that efficient. So what we came up with is a method that can actually extrapolate the learning curve. So we can basically just predict how the accuracy will unfold over the training epochs. And then based on the predicted epochs, right, so this learning curve predictor is transferable across different data sets, different hyperparameter settings, and we can actually use that to predict the learning curve, and then use that to select the hyperparameter. And in addition to that, we also consider the different human preference. Maybe one user may want to obtain just the best performing model, regardless of the cost, training cost that's put into the model, right? Or another user may prefer the model that performs less, but takes a lot less steps to train the model, right? So there are some preferences, right? So considering all of that, so we were able to obtain the models that ranked better than all the other hyperparameter optimization approaches. But there are still some challenges in applying this to large language models, because the learning curve extrapolator should actually obtain a lot of learning curves in order to be reliable. So we are trying to make use of some synthetic data to better learn the learning curve extrapolator for the training of the large language models. Another approach that we have proposed is an AutoML agent. So this is like a multi-agent large language model framework that can do full pipeline AutoML. So basically, given some input description of the problem that's given in natural language by the users, we can translate that to a structured problem for like a search for that requires the training of the model by searching for the optimal data set and search for the optimal model, and then generating the deployable model and the code, right? And in this result, we can see that our method is able to generate deployable code for with really high success rate that's close to 1, while the baseline models such as GPT-4 or DS agent fail to do that. Okay, so far I have discussed about the enhancing the training efficiency of the GenAI models. But as more GenAI models are put into the production and service, the focus is shifting more toward enhancing their inference time efficiency. I mean, in academia, we are still concerned about the training efficiency. I know that. But for industry, where they have AI systems that are targeted toward like thousands and millions of users, we also want to reduce the serving cost as well, right? So there are the standard approach to enhance the inference efficiency of the GenAI models is to make them smaller. So we can use pruning, quantization, and knowledge distillation. So we are also working on this direction as well. So we have worked on the compression of the like a T2I model. So the idea is to do the layer pruning, because all the other types of pruning, like a weight pruning, structural weight pruning, they don't really work. They don't really reduce the latency. They don't really make the model to be faster. They don't allow them to consume less memory. So the layer pruning is the most, I think, the prevalent approach and the most dominant approach for pruning out the pre-trained transformer models. So we were able to obtain like a 3 times smaller model that's like 5 times faster, but by reducing out removing the layers while doing the knowledge distillation for the self-attention layers. So what we have realized is that the self-attention layers are very important in transferring the knowledge of the original teacher model to a smaller student model. And recently, we are also exploring the sensitivity of each layer to pruning. And we have been aware that we found that the different layers have different sensitivity to pruning. So when you do the layer pruning, we can't just do the layer pruning 10% at random layers. Because some of the layers, such as the input layer, or the layer that's close to the output, are more sensitive to pruning than the middle layers. I mean, for the middle layers, you can just prune a lot of them, and they may just obtain the same performance. Or what we also tried is like simply just copy and pasting, and the middle layer across like multiple layers, and they also do not affect the final performance of the model. But the layers that are close to the input and the output are very sensitive. So we are trying to come up with a way to actually measure this sensitivity using some kind of proxy and use that when improving the layers. And like a noise sensitivity. So instead of using actual data, we can just use the noise and perturb the noise and see how sensitive each layer can changes over the given layer, given noise, right? Another approach that we are exploring is the population-based model compression, because there are so many good compression methods out there. So instead of just coming up with our own pruning method or own like quantization method, we can just combine multiple of them, right? Generate a population of like a generate different combination of the different like compression techniques, and we can simply just evaluate the final performance of the model using a very lightweight benchmark or a performance predictor. So this is our ongoing work on population-based model compression. And I'm going to now introduce the main part of this talk. So we have built an efficient attention mechanism that can replace the quadratic attention mechanism of the transformer models. So the transformer is the dominant architecture for the current generation of the GenAI models, but the main bottleneck is the attention mechanism because it has a quadratic complexity to the number of tokens. So there are some approaches to handle that. So first is the better hardware-aware implementation, such as like a flash attention, page attention, right? So flash attention basically allows you to just process the attention in blocks. The page and page attention allows you to just do the KB caching in non-contiguous regions of memory, right? So they are kind of like a system-based approach to accelerate the computation of the attentions. But there are also better algorithms that gives you just like a low-rank approximation of the weight matrix. So you can like decompose the QKB matrix into some linear approximation, right? Or we can come up with a sparse attention mechanism such as Big Bird that tends to have the attention only across the very local tokens and like random attention across like tokens that are far away, right? And there's like a reformer. There are like a lot of like algorithms that have a better complexity, like a linear complexity, like a subquadratic complexity. But the problem is that they all fail to obtain good performance. So they are not really mainstream approaches. So flash attention, page attention became mainstream because they maintain the original performance of the attention mechanisms while making them faster. But these methods obtain much worse performance compared to the vanilla transformer model. And they also require to train the model from scratch. And I think this is the reason why such like a linear complexity model such as Mamba has not become so popular. So you have to just train everything from scratch, right? So right now, so people are now realizing that for the speed of the computing the transformer model, doing the inference with the transformer model, what's the most important thing is making it to be more memory efficient, because the memory bandwidth and capacity are like the critical bottlenecks, right? So flash attention eliminates the bandwidth using the blockwise like computation. The page attention remedies the KB cache memory fragmentation issue. So they are all adapted in accelerated large language model serving platforms such as VLLM. But we wanted to come up with an algorithmic way to make the attention to be faster. So we first came up with a sparse linear attention that does not require training from scratch. Because we thought that the main reason why all the previous methods failed to be adapted in industry was because they require training from scratch. So if we can just convert the quadratic attention of the pre-trained transformer into a linear attention, then that has much larger potential, right? So what this method does is that given some quadratic attention from the original model, it predicts the sparse attention matrix in linear time. So we have the attention estimation model, which is basically a small CNN that generates this output. And then we also have a knowledge distillation step to make sure that the generated sparse attention matrix have the same output as the original quadratic attention transformer. So this model was able to to maintain the performance of the original model for a smaller context size, actually. It was able to reduce the memory requirement by making the attention mechanism to be linear and sparse. But the issue was it resulted in increased latency. So there was some trade-off between latency and memory. So we were making the model to be smaller, and we were making the model to be more efficient in complexity, but the latency went up because it has so many components. So we did we actually try to study what the issues were, and the performance predictor were quite slow. So we had to predict the attention map estimator was working quite slow. And there were many other parts that added up to the latency, right? And another thing was that it requires fine-tuning for knowledge distillation, right? And the data also, what kind of data you have, also matters when considering the final performance of the distillation, right? So we came up with another method that does not require any training at all. So this is a training-free, log-linear sparse attention mechanism that recovers the original performance with a minimal loss, with the hierarchical pruning that explores attention locality. So what this means is that there are some locality in the attention scores. So that means you don't have to compute the attention score between all the tokens, right? You can, if you just compute the attention score for just one representative token in each chunk, we can just safely disregard a block of tokens at a time. So you can drop a block of tokens and just ignore the computation on this block altogether. But how do you select the most representative token? We found that the attention scores differences depends on the actual distance between the tokens in their positions, right? So that means if you are given a block, you just have to select the middle token, right? And then just compute the attention score from that token, and then use that to remove a block, right? So we have some theoretical analysis on this too. So that kind of makes sense. So we were able to just avoid computing the attention scores for some of the blocks altogether. And we do it in a hierarchical manner, right? So we get rid of some of the least important blocks. And then in each block, we also do this in a recursive manner until we get the final attention for the most important blocks, right? So this will have the complexity of OT log T, where T is the number of tokens. And this is not only good in terms of the computational complexity, but this means that we only have to have this we only have to compute the attention score for some of the tokens. So that means most of the other tokens could be offloaded to slower memory, like CPU memory, DRAM, right? Where we only keep the most representative tokens in the cache. So this will make the model to better explore the memory, and we can see that it's much faster and compared to the flash attention as the token length goes up. And by making use of the KV offloading, we can deal with the tokens that do not fit into the memory, while the flash attention doesn't do that. So flash attention just processes the attention block by block, but it doesn't really make use of this uneven importance between the tokens. So our method achieves about 17 times speed up on the attention kernels, but and 4 times 3 speed up over an end-to-end LLM decoding framework, and especially with the larger speed up when the context length goes up. So when it becomes like a millions of tokens, it does even better. And because its context window size is so long, so it can actually run the long-term dependency across different tokens. So like the streaming LLM or the other approaches that only has the local attentions cannot model such long-term dependencies, but our method is able to do that, and is able to recover the summarization that's close to the human ground truth. I'll just skip the video due to the time limit, but it just shows that its decoding speed is really fast. So this is actually integrated into our LLM serving platform for our startup, Divoro.ai. So I'll discuss some of the future research direction. The first is the training-free context extension with the HIP is that we can actually increase the sequence length a lot further, but the problem is that the positional encodings do not extrapolate very well. So that is another issue that we need to take care of, and we also need to consider the context extension to the unseen positions. Another thing is that because we have made the attention mechanism to be so efficient, now attention is not the bottleneck. But the MLP layer, the fifth network layer, has become a bottleneck. But this layer has been used since like the 1960s, right? So we need some new invention that can replace the MLP layer, but nobody has actually focused on this because the attention was the bottleneck before. But with this, our HIP attention framework, we need to come up with a way to make the MLP layer to be faster. So we are trying to decompose the weight into the sparse and low rank matrices, where the sparse part considers deals with the permutation of the features between 2 layers, and the low rank matrices takes care of the transformation of the features. Okay, so we also proposed a way to extend the context window size called cascading KB caching. So there is like a method called sync attention and like a streaming LLM that basically has a sliding window approach to attend to the tokens. So, but the problem here is that they can only capture local dependencies across the tokens. So if there are some very long-term dependencies across tokens, then it cannot model because it forgets everything that was given to the model previously, right? Because they evict everything in the first in first out, right? Based. So instead of doing that, we made a cascading eviction strategy such that the ones that have a lower attention score are going to be evicted with a higher probability. The ones with the higher attention scores have a higher chance to be kept, but they are moved to a exponentially smaller cache. Right? So we have a cache size, the original cache size, and the cache that is half the size, cache that is 1/4 the size, and so on, right? So if a token is deemed to be important, that token will survive through all this eviction cascade, right? So this cascading cache will capture some long-term dependencies across the tokens, so it's going to perform better when we need to deal with the longer token sequences. So given the same cache size, it has a stronger performance on the long context task. So if you look at the performance on the long bench, so this model works a lot better compared to the baseline models such as streaming LLM or like a BigBird. So BigBird actually works pretty well. So BigBird have the local attention cross a random attention across different tokens, regardless of their like positions, and that works pretty well. But still, our method works a lot better. And our next approach to actually consider any context length is to have this local window while doing the log n search using some kind of hashing, locally sensitive hashing in this domain. So this is a kind of a combination of the RAG strategy with the long-term, the long context window modeling. So we are working on this using the hashing technique. So with some kind of like the tree structure that can be searched in logarithmic time. So this means that any token that was observed in the past has a chance to be retrieved later. But because we have lowered the complexity to log n, so it's going to be much more efficient than it's going to have a chance to be retrieved, right? With some complexity, right? Because the previous method either kept the token or just evicted them completely, right? So this always find those like tokens that are evicted from the cache using this log n search. Okay, so this is the end of the talk. So throughout by proposing this talk, so we have proposed some solutions to enhance the training and the inference efficiency of the GenAI models. So the solutions that we have developed have the impact of lowering the cost, so making the GenAI models to be more accessible, to be more adapted by the industry, so lowering the barriers to entry, and allowing GenAI to solve larger problems that the current generation of GenAI models were not able to solve. So we are planning to build the video language models that utilizing the strategy that we have built to enhance the training and efficiency of the GenAI models. For like a movie, they can take care of really long videos with huge resolutions. Or the videos with really redundant frames, such as the egocentric videos. Okay, so that is the end of the talk. So if you have any questions, then feel free to ask.
Thank you so much. Questions? By the way, the last thing that we are working on this, we should talk more about.
Yeah.
Yeah, please.
I think you mentioned for the linear model, you need to. I think you just mentioned that for transformer you need to train from scratch, but for linear model you don't need to. Can you elaborate on that? What do you mean?
Okay, so basically this is a method that can predict the attention map, a linear attention map from a quadratic attention matrix. So you can actually decompose the attention by rearranging the matrix computation, right?
So it's like you're converting the quadratic model to linear?
Yeah.
Okay.
So instead of just making it to be a token times token, it's going to be the latent dimension times latent. So it's basically just reversing the order of the matrix computation, but it's going to be less accurate if we do the linear approximation.
So it's like there's a trade-off between accuracy.
Yeah, that's why actually that's one of the reasons why we switched to the n log n attention mechanism, because that is more accurate than the linear attention mechanism. So linear attention mechanism, when the context length goes up, becomes increasingly more inaccurate.
Okay.
Yeah.
Thank you. And another question is, you mentioned that for the graph, it's like you just select the middle one, the token.
Yeah, right. This one, right? Yeah.
Yeah. I wonder how many tokens in that range do you select the middle one? Is it?
Right. So if the window is too large, right, the selected token may not be the most representative, right? So what we are saying is that it doesn't really necessarily mean that the middle token is going to represent the attention importance, the importance of all the tokens, but it means selecting the middle token is the optimal strategy compared to selecting all the other tokens when you compute the overall attention score for the block.
Okay, I see.
But if the bucket is small, right, then it's more safe to just remove the block. If the bucket is large, then we may have the risk of dropping out some important tokens. So we are actually trying to come up with a way to fix this problem as well by actually making so when we do this hierarchical pruning, right? So we just have to start with small enough blocks, right? So we don't just start with a very large block, but we start with the small blocks in the beginning, and that's going to fix the problem.
Is the window size fixed for selecting the middle one?
No, window size gets smaller and smaller because it's a hierarchical. So within the selected bucket, right, selected slot, we hierarchically divide it into smaller blocks, right, and then decide which blocks to preserve and which blocks to drop in a hierarchical manner.
Thank you.
Yeah.
All questions?
Okay.
Sorry, I know this was in the beginning, but can you talk a little bit more about weight visualizations?
Is there some error? Here? Or
Yes, a little bit. This slide we're going for.
you mean the weight initialization?
Yes.
So the problem is that when you initialize the weight, right? Some of the randomly initialized weights start from this valley, right? Where it could be where you start from some kind of a local minimum, right? So it's almost impossible to get to the optimal solution from this area. So where how you initialize the weights have really large impact. Some of the weights are not going to be updated, right? Over the course of training. So that is why the log-tail ticket hypothesis came out, right? You train the model and then you do iterative pruning, and it's going to obtain the same, and then you reinitialize the weight back to the original weight, and then train the model again. Then it's going to obtain the same performance as the model with a full set of weights, right? Because some of the weights were not really contributing to the model performance at all, right? And they are really not being updated because some of them just got sparsified and they don't get any signals, gradient signals to update them. So all of those problems are happening because you do random initialization. You should actually, if you sample the weight, because we learned the distribution of the weight, and the weights are sampled from a high density region, right? So you have very little chance of sampling them from those poorly initialized regions, right?
And then when you run the evolutionary search algorithm,
Yeah.
do you have to get the fitness metric?
Yeah.
Do you have to rerun the generated weights?
No.
Again?
So because this fitness evaluation is done using our predictor. So we assume that we have a way to predict the fitness of the generated solutions, and we have some performance predictor that works in the latent space of the neural network weight. Neural network, actually, so we have a paper that's accepted to NeurIPS this year on this. So this is like a set-based neural network encoding. and it can predict the performance of the model in the latent space without having to train it on the actual data set. So given a data set and a encoding of the neural network, it's able to predict the final performance very reliably. So we can use this to select the latent code of the neural network that may work well. And this could be used to guide the sampling process and the latent optimization process and many others, like the selecting the optimal candidates, right? Okay.
That's very cool.
Taylor? Maybe come to the front.
I have a quick question also about this, the model sampling and also the model generation.
Yeah.
So just wondering, so in both this process, we have like a predictor or some model to guide the generation or guide the
Right.
sensing. So and those are also like neural network deep learning models.
Yeah.
So I was thinking that is that able to use the same strategy to update the guidance model? Because they're also neural network models using a bunch of way we train.
Oh, okay. So you can actually update the predictor weight using this latent space optimization.
Yeah,
you can do it forever, right?
It is like called self training. I think in many areas we do use this method because I think in the if we like keep doing this, you will definitely go over overfitting to itself. But if we just do a few epoch, it could potentially learn something, discover some.
Yeah, I mean that's a very good idea. Never thought about it, but I think that makes sense.
Yeah.
So
if they're also like
because the performance predictor is also a neural network in itself, right? You can also have another performance predictor, maybe guiding the generation of the weight for that performance predictor, right?
Yeah, like or even use the predictor itself to provide
yeah,
the
we can
supervision.
actually use the predictor itself. But actually, the performance predictor is based on some set-based neural network, and a little bit different, right?
Oh, yeah.
From the one that actually generates the
Yeah.
neural net. Yeah.
Yeah, but I think maybe some other like similar predictor could provide the signal.
Yeah, right. Yeah, I think there will be a way to do something like that. Although we never tried that before, right? That's a very good idea. Yeah.
Yeah, thank you. And
Yeah.
Do you have more questions? Maybe take one last and then we close
Okay.
this.
Yeah.
Okay, I will take the last one. So you have a figure showing, it's over here. You have different optimizations, and the weights you generated can save you fine-tuning epochs.
Yeah.
So why could that happen? Because you learned the weight generator from pre-trained models.
Right.
But actually you can do better than pre-trained models.
Oh, where? Here?
The training, fine-tuning epochs, pre-trained
Because
models.
the pre-trained model is just a single pre-trained model.
Okay.
So neural network weight generator is trained on a lot of pre-trained models.
Okay.
So it actually has a transferable knowledge across different
models.
pre-trained models. The pre-trained model, you have to select a single pre-trained model and then do the optimization.
So the generated weights, their performance, could it be capped by the best pre-trained model, or actually it can go beyond?
No, actually, much better.
It can go
Because
beyond.
the best pre-trained model is not going to be the best combination of all the pre-trained models, right? And also because some of the pre-trained models have some poorly initialized weights that do not really contribute to their performances. But the sampling strategy mostly just ensures that we select good weights. So, I mean, if you try to prune the model, right, you cannot prune it. If you prune it, then you get really the sharp drop in the performance. So that means they were initialized better, right?
Great, thank you. Amazing work, a lot of work.
Yeah.
Thank you.
Yeah, thank you. Yeah.
Thanks, speaker again. Thank you.